I want to talk about the definition of Rushworth's doubled Khovanov homology. At least to motivate what the idea is and to play with it a little bit. So this is a solution to Khovanov homology for virtuals over the integers. And it's a different solution than Monturov's, or the one that we modified from Monturov, which we've talked about some. So let's recall, before I give you show you how he changes things, let's recall the basic problem, which we've talked about quite a bit, but we've had a little hiatus, so let's just recall it again. The basic problem comes from the fact that in working with virtuals, you can have a single cycle map. Sorry. You can have a single cycle map. And we decided to take eta equals 0 and adjust accordingly. And you'll see that Rushworth does a different, decides to take eta not equal to 0 and adjust accordingly, and we'll see how that works. But I want to recall first recall what we need to examine. So let's recall it again. Sorry. Something behaving strangely. All right. Maybe it's this bit of metal. So I'm looking at a specific complex. Now, if we re-smooth the top, then it's eta. And if we then resmooth this one, it's still eta as well. So that's possible to have two etas in a row like that. And on the other hand, if you go here, you have a delta. And that came from this one. And then you're going to multiply here. You go that way. And then what was our problem? Our problem was going to be in the following way. Actually, since I'm going to write on this slide, I'm going to overwrite on this slide, not just our problem, but also Rushworth's solution. So let's just give ourselves a little room. But what we ran into was the following. We might start with 1 here in the usual, we'll work in the usual Khovanov algebra. And then we have, remember, we have x squared equals 0, delta of x equals x tensor x. I'm sorry, delta of x equals x tensor x, delta of 1 is equal to 1 tensor x plus x tensor 1. And you don't need to know about the epsilons and so on, and 1 behaves like 1. Yeah, so that's the basic Khovanov algebra. And if you started with a 1 here, then we would have 1 tensor x plus x tensor 1 here. And then you would multiply, which means you add the products there, and you would get 2x. But if you went this way and you got 0, well then, what did we do? We changed the algebra rules to local coefficients, etc., and made this composition 0. And I won't recall the details of that for you right now because we've been over them many times. And you know, there's a number of intricate points there, but one was able to get some nice theorems out of it by formulating it that way. And you might wonder, well, maybe there's another way to do this altogether. And that's what Rushworth did. Rushworth created another way to do it altogether. And let me show you his idea. So for that purpose, I'll use the same setup to discuss with, but we'll do it a little differently. So let's erase all these comments and think about it again. Now, if we kept the algebra more or less the same, why then we would want to just get 2x over here and not make it cancel. Yeah, that would be what we might have in mind. But then we're going to try to do this with a non-zero eta. And so I want to write down Rushworth's idea over here on the left, and then show you how it's working. So we're going to Rushworth. We will double the module. That's why he calls it double. Double the module. So we have if the module was V, then we're going to have V upper and we're going to have V lower. Never mind about grading. We can work out grading later, but we have 2 copies of the module, 2 copies. And as far as multiplication and co-multiplication, take VU into VU and VL into VL as usual. No change. But we're going to define eta, and eta will move between. The modules. Now I'll be quite explicit about this in a second. So I'm going to tell you the formulas for eta here. Eta applied to 1 in the upper module is equal to 1 in the lower module. Eta applied to x in the upper module is equal to x in the lower module. Sounds more or less normal, but now comes the more interesting part. Eta in the oops, I have to make sure I'm telling you the story for the right algebra. Just one moment. You don't want to go telling you the wrong story. Eta for the x in the upper is the x in the lower. Eta for the 1 in the lower is 2 times x in the upper. And eta in the x for the lower is equal to 0. Now, this may seem very mysterious, but in a moment, you're going to see that this exactly solves our problem for this square that we would like to commute. Let's take a look. Suppose that let me try a different color so it's easy to see what I'm doing. Okay, so suppose I start with 1 upper here. Then under eta, it goes to 1 lower over here. And then 1 lower under eta goes to 2x upper. You see? That's what we wanted, right? Because if we went around this way, we would go by delta to 1 upper tensor x upper plus x upper tensor 1 upper. And then we would go by multiplication here. And lo and behold, it worked. So by exchanging back and forth between the 2 modules, we get the answer that we wanted. Now, what about the other one? What about the lower? Well, let's do it all around the outside in my picture. Let me get myself enough room so you can see. I'll do it in blue. So now we're going to try 1 lower here. So 1 lower goes to 2x upper. X upper goes to x lower, just exchanges back. And since it got multiplied by 2, it will end up at 2x upper. And of course, that's also what I wanted, right? And now, what about putting an X through this system? Let's get another color and put an X through. Maybe black. Sorry. Get my pen in order here. Okay. So suppose we considered X upper here. Well, X is, when you put in an X, or maybe I'll put it down in here, X upper. X upper goes by delta to X upper tensor X upper, which goes by multiplication to 0, right? That's the Khovanov algebra. We're in the Khovanov algebra, X squared is 0. Now, according to these eta rules, X upper goes to X lower, and X lower goes to 0. You see? And now, if it had been X lower here, well, X lower goes to 0 immediately, and then it will compose into 0. So that works as well. So as you see, this solves our problem square. It solves our problem square, keeping the Khovanov homology doubled in this way, with most of the structure the same as before, and extended to doing the eta to walk back and forth between those two modules in such a way that we get commuting squares. Getting commuting squares means that we can use our usual conventions. We can use the usual sign conventions. For the homology. So that's the basic idea of the Rushworth doubled Khovanov homology. And I have included in the Dropbox a copy of Rushworth's paper, basic paper on this. You can take a look at it, and you will see that there's quite a lot that you can do with this. What I'm going to do today is talk about some details about this in relation to the Lie homology. We're not going to penetrate this very deeply, but as you see, this is a very interesting idea that avoids the local coefficient complexity that we had seen before completely. And one thing that I do not know very much about, nor does Rushworth, I believe, or anyone else at the moment, is what is the real comparison between the Montura version, or our modified Montura version, and Rushworth's version. We can see some differences in the formalism, but what in the end is the real difference between these? What will computations of this look like? This one can certainly be computed in a way exactly analogous to the way people have computed Khovanov homology. And it's just a matter of time before someone, perhaps some of our group, gets a computer program working to take a look at this in detail. I think things have been a little slow in evolving computer programs for this one. We understand why the other one was going slowly because of its intricacy. This one is not essentially more complicated to write a program for than the original Khovanov homology, for which there are programs. So we might summarize this in another slide, just so you see how this works out. That's my other slide. Let me remove the diagram. And just behave algebraically with regard to this. All I'm doing is rewriting the flowchart of what happens. You see, if you had an upper and you applied an eta, then you would get an upper 1. And if you applied an eta again, you would get twice x mu by definition. If you had a lower and you applied an eta, then you would get twice x upper, and then you would apply the eta, and you would get twice x lower. And so And so you see, those are exactly what you wanted in the double eta composition around the square. And then on the other hand, if you had an x left, it would go to 0 immediately, and then it would go to 0. And on the other hand, if you had an x upper, which also ought to go to 0, it will go to x left, lower, excuse me, and then it will go to 0. So in both cases, it will go to 0, and that's also what you wanted. So you can see from this that if someone had the idea of doubling the module and wanting to figure out what the eta should do in relation to the doubled module, it's pretty nearly inevitable, since you know what you want down here. You want twice, and you want 0. And so what else could you do? So his discovery is dependent primarily, I think, on the idea of doubling the module to try to get a structure that would hold this. Now, it's also certainly a good question to ask whether there is another reason for this. But I don't at this stage know what the other reason for it might be. I mean, perhaps there is a geometric reason for this, or perhaps there's a reason that's related to virtuality that we haven't quite understood yet. Why did this work, and how would you come upon the idea from some other way of thinking? It's relatively new, just a few years old, and I think it needs a lot more understanding from that avenue. So that is, but that's what it is. It's a nice idea, not a complicated idea in the end, and workable. So let's continue. Comments or questions at this point? Okay. Then let's recall the Lie algebra and see how Rushworth is going to work with regard to the Lie algebra, which is the other kind of Khovanov homology that we have been discussing, the simpler one. In the Lie algebra, the one without any extra uppers and lowers, we had x squared equal to 1. We have delta of 1 is equal to 1 tensor x plus x tensor 1. We have delta of x is equal to x tensor x plus 1 tensor 1. And we have epsilon of 1 is 1, and epsilon of x is 1, and epsilon of 1 is 0. And that's still a Frobenius algebra, and it satisfies our criteria for getting a homology theory and everything. And we've talked about it before. So the Rushworth eta, it's doubled again, of course. And the Rushworth eta is as before. Eta of 1u is equal to 1 lower. Eta of xu is equal to x lower. Eta of 1 lower is equal to 2x upper, and eta of x lower is equal to 2 times 1 upper, not 0. It's a little different. That's our eta. And now let's take a look at the usual problem square again for this. Now you can remember that our problem square, so I don't have to write the diagrams again, goes by delta and m and eta and eta. So with that in mind, let's try some things out and see what happens. So I could start with one upper, and then I will end up at one lower, and then I will end up at 2x upper. Right. Now, if you go through in the Lie algebra around this setup, then you will go to one tensor x upper. Let's give ourselves a little room. One tensor x upper plus x upper tensor 1, and then that will be multiplied, and this will go over to this exactly, right? And the same will work in the lower. But now what if I had an x upper in here? Well, then x upper goes to x lower, and x lower goes to 2, 1 upper. Now let's do it the other way around. Here's where I hope my algebra works, right? So I'm going to do delta on x upper, and I get x upper tensor x upper plus 1 upper tensor 1 upper. And now I'm multiplying, but aha, you see, 1 times 1 is 1, x times x is 1, and 1 times 1 is 1, and I get a 2. So it works, you see? So that's enough of exercising with this. It's working. And that's what we need to do to modify the eta in the Lie algebra. So this is for Rushworth-Lie doubled. And now we have another nice exercise to do, because you recall that the Lie algebra can be written in terms of the color elements red and green. So let's see what happens with them. Yeah, okay. Just wanted to save my slides. So that's a new slide, and we could remove this and keep the other part. Okay, so what was the story about the red and the green? The story was red is going to be 1 plus x divided by 2, and green is going to be equal to 1 minus x divided by 2. And then we have, from the usual Lie algebra, we have that green squared is equal to green, red squared is equal to red, red green equals green red equals 0, red plus green equals 1, and the coproduct of red is 2 times red tensor red, and the coproduct of green is equal to minus 2 times green tensor green. And this is a very pleasant way to think about what the Lie algebra is doing. You can identify cycles in it by the fact that red times green is equal to 0, and that will, when you have separate circles, make the boundaries go away and so on. All sorts of nice things by using that change of basis. What happens to our things under eta over here? And I'm going to write the answer, and then we can do a little work on the next slide checking it. So I claim that eta of RU is equal to RL, that eta of GU is equal to GL, and that eta of RL is equal to 2RU, and that eta of GL is equal to minus 2GU. Okay? And that will follow from this with these definitions. I think it's worth doing this exercise a little bit, and you could have some fun doing the rest of it yourself. But let's look at our problem square from the point of view of this eta, and these if we had it in mind. So suppose you're at the top of the problem square and you had a 1u, right? And you went this way. Oh, I don't mean a 1u, I meant an r. Let's do it in the color coordinates. So suppose you're up at the top of the problem square and you have an RU. Okay, now you do an eta. Well, this gives you an RL. And now you do another eta on RL, and you get 2RU. Now, here you're going to do a delta, and delta of RU is 2RU R tensor RU. And then you're going to do a multiply, and R times R is R, so RU times RU is RU, and so this commutes, you see? So, so I'll just put a little check mark next to that, and you can have fun doing the other exercises that show you that all the trouble squares will be working out correctly this way. Okay. So let's see. My only oh, I know. Let's make a new one and call it 7. All right. That way we have access to these equations if we want them. And now let's do a bit of an exercise. Let's see. Let's find out about eta of R. I'll just do 1 and leave the rest for you. Eta of RU. Yeah. So in order to find out about eta of RU, I need to take eta of 1u plus xu divided by 2, because that's what RU is. And now I go back to my equations, and I have that eta of 1u is 1L, and eta of xu is XL. And so this will be this divided by 2, which is, of course, RL. And so you see we have eta of RU is equal to RL. All of these are of that ilk, but there are some that have a little sign changing in them that are related to this sign change here. And so I will just say exercise, check the rest. Okay. So now we have the following situation. If we if we take a virtual knot or link, let's just take a projected diagram, and I'll just choose one at random here, and put some virtual crossings in it somewhere. Too many, maybe. Maybe I'll take that one out. Then, and of course, the crossings could be any old way, but you can always color one of these in red and green. Now we have no cut points, so we just simply color directly. Red came from here, red, green, red, green, red. And if you had oriented this diagram, you would probably, I just chose it at random, so I don't expect that it will work well with regard to the, but in fact it did. No, it didn't. Yeah, so you see, if you do a cipher smoothing here, this is a cipher smoothing, it doesn't respect the coloring. And remember what we found in the other system was that after the cut points were placed and you did a coloring, then the ciphered smoothings would carry the coloring, in the sense that respecting the coloring means that if you had 2 reds and 2 greens and you took this smoothing, that would be a color smoothing. And what we found before was that ciphered smoothings and color smoothings were the same when you have the cut points. But when you don't have the cut points, then you will have a different interrelationship between the color smoothings and the ciphered smoothings. And this is exactly what we had in that invariant that I called the binary bracket for knots and links, so that the states of the binary bracket correspond to these colored states for thinking about the Lie homology, the doubled Lie homology, when you put in the doubled variables. So the doubled Lie homology carries the colorings without the cut points. And if you were to smooth one of these according to, let me put in the smoothing markers so you can see them. Right, so this one happened to be a ciphered smoothing and the other 2 were not. And then this, then let's take a look at this as a state and see what we can see about it, just as working this example. If I have room on this slide for it, but I do not. So I'll let it go and put it on the next slide. All right. So on this slide, let's do the smoothing. Only I don't really want the orientations either, so let's get rid of them. Okay. And now. Oop. So in this case, as you see, this is a cycle in the Lie homology if these were A smoothings. So this could be a cycle in the Lie homology in an appropriate choice of crossings in this link where these would be A smoothings. And so when you multiplied, you would be applying the differential, and every single one of these is RG, and so is 0. So that's what I mean about producing the differentials in relation to this and seeing how. Now, exactly when things are going to classify as cycles and computing the Lie homology is a little more complicated than it is in the classical case. And I think I will just come back to that next week and we'll talk about that. And we'll also talk about how the colorings are related to the states of the binary bracket. But there you have a beginning introduction to the Rushworth homology. So I'm going to continued next week. On this topic. And if you're interested, take a look at the paper, which I've included, Rushworth's paper, which I have included in the Dropbox materials. Comments on this? Okay. My second topic for today is some work that's ongoing right now with Nestle Hangugumsu. And it has to do with marker states for the Alexander polynomial. And I'll explain for a little while about that. Come on, into my desk here. So I'll call these marker states. And I think we talked about them before, but let me remind you how it goes. If you have a closed classical knot diagram like this, then the number of regions is equal to the number of nodes plus 2. And that's a nice exercise using Euler characteristic. So if I were to knock out 2 regions, then it's possible to have a one-to-one correspondence between the nodes, 3, and the remaining regions. And so I can do the following kind of thing. I can choose to mark from this region that node. I can mark from this region this node, and I can mark from this region this node. And I call that a marker state. So a marker state has exactly one marker per region. And this is of interest just at the level of the combinatorics of knot diagrams, because you can do the following. You can smooth on a marker like that. So you can smooth the whole diagram. All right, smooth for smooth, I guess. And then what will happen here? You will have this. And you see that you get a single Jordan curve. And there is a one-to-one correspondence between marker states for a choice of stars and what I call Jordan-Euler trails. On the diagram. That's what happened here. This is a Jordan-Euler trail. What I mean is it's a Jordan curve, but it's also an Euler trail on the graph of the knot. Here's just the graph of the knot. An Euler trail on the graph of the knot in the sense that it is a walk along the diagram which uses every edge once and never crosses at a crossing. So you could, I remember long ago seeing a puzzle book when I was thinking about this and realizing that puzzleists independently had discovered this as a nice puzzle about a planar four-valent graph that you could take as a puzzle for a planar four-valent graph. The following puzzle, let's just draw one and contemplate it. Somebody hands you a planar four-valent graph, and it could even have more than one component. And they say to you, well, think of this as a system of roadways, and you are asked to walk along this roadway, starting somewhere. And when you reach a crossing, you have to turn. You can't go through the crossing. So like you could go this way, and then you could go this way, and then you could go this way, and so on. And you keep on going like that, and you must use every road in the entire roadway and come back to where you started. That's a puzzle. Actually, it's interesting. Let me show you this. Find it. Yes. For many years, I thought that the puzzle was of recent origin, and I had encountered it maybe in a puzzle book, one of those little books of puzzles that you can buy in a store. And then recently I'm searching my own library, and I have a book entitled The Magic of Lewis Carroll, which is a book about Carroll and things that he did by a person. What was it by? By John Fisher, and a man named John Fisher. The Magic of Lewis Carroll by John Fisher. And I'm browsing in this book, and I come across the following. I'll read to you. In Collingwood's Life and Letters, Isabel Standen recalls being shown by Lewis Carroll, on August 21st, 1869, a puzzle so thoroughly characteristic of him in its quaint humor, in which one had to draw 3 interlaced squares in one continuous line without ever going over any parts of the line twice. So he set up the following thing. He said, oh, sorry, let me put it down there. A square. Yeah, and a square. And a square. There. And you're supposed to draw this and follow the instructions that I just gave you, basically. I had to draw 3 interlaced squares in one continuous line without going over any parts of the line twice, and without intersecting the line, and without taking the pencil off the paper. All right. So the puzzle actually goes back at least to 1869 with Lewis Carroll. I'll write those references into the notes when I rewrite these notes, okay? But then some people probably thought about this. How would you do it? Well, I ask you, how would you do it? I already told you what kind of a thing it's in one-to-one correspondence with, but what if you were only just trying to do it? Well, you can do it in the following way, of course. You could say, I will just arbitrarily smooth this. And then I will arbitrarily smooth this. And if I get in trouble, then I'm going to be more careful just to get a solution. But of course, this is not something you could do while driving your car on the roadway. That's another matter. But what kind of trouble could I get into? Well, I can get into trouble right here. I can't arbitrarily smooth this, or I'll create a disconnection. But I can smooth it. That's the situation that will always be. You start with the graph connected, and you keep on going in this fashion, and you make choices. And if your choice gives you a difficulty, okay, but it may not, and then you'll have more than one choice. But near the end, you may have some that could conceivably give you a difficulty, but if one disconnects, the other will connect, as you can prove for yourself if you care to. So I will get to an example in a moment, I'm sure. I have a reason for drawing an example here, so we'll just do this. Here's another one where I have to choose it in the right way. See, here's an example. If I do it this way, it disconnects, but if I do it the other way, it connects. And you could prove a little lemma to that effect in general about the situation. And then this is how to get all of them, of course, by going through what amounts to a skein tree of choices. So all of that is going back quite a ways to find such things. Let me finish drawing this, and then you'll see why I'm going to do that. Oops. I wanted to tell you about, let's just erase those and then make the choices. So let's say we do that, and we do that, and we do that, and we do that, And now I have one that I better be careful with. Let me see. Somebody's going to be disconnected. Yep. If I do it this way, it'll be disconnected, but this way it's connected. So there it is. Now I want to show you how you get the markers from one of these if you had one. You put a marker in one region, and you put a marker in an adjacent region. And now you start growing a tree by going from the marker, from the star, through the doorways of the smoothings that you made. I've grown a tree. The tree goes into half of the regions in the diagram. I mean, not numerically half of the regions in the diagram, but the half of the regions that are on the outer side of that Jordan curve that you're looking at. Now you put a marker in every time you go through a doorway. And that will uniquely mark the region as you entered it. And all of those regions have now become marked. Now that's only half of the story. I do the same thing on the other star. And I put markers in those regions. Every time I go through the doorway entering a new region, I mark the region that I entered. So all these markers are actually pointers back to the root. And that is how you get a marker state from a Jordan trail. And you can enumerate the marker. You can enumerate the trails by just trying to enumerate them all if you like, or you can enumerate the marker states. Now, the reason I'm going through all this is because this interesting piece of research that we're in the process of doing at the moment generalizes this, but how it generalizes it, I'm not telling you just yet. I will in a little bit. And of course, I think I told you before that these states can be seen to underlie the Alexander polynomial, but also the Jones polynomial, and also the Oswath, Szabo, Heckard, Floor homology link invariant. I would really like to understand these states better in relation to what they lie under. And so that's the reason for talking about this. And let's continue now. So this is a big example of how this works, but now let's go back to a smaller example. Let's go back to the trefoil knot example. I'll stay on this page. In the trefoil knot example, trefoil diagram example, we had this. Oh, I'm so sorry. We didn't have that. We had this. And there is a way to go from states once the markers are in to other states, which is very local and combinatorial. And I show it to you here like this. I take a marker and another marker that are adjacent across an edge, and I rotate one of them into the other region and the first one into the second region. So they just exchange the regions that they were pointing to. And I may write that by putting a little rotator here to indicate what it is I have in mind to do. Yeah. And that gives me another state. So in the case of the truffle knot, you see that we could have rotated here. And we could also have rotated here. And in one case, we rotated counterclockwise to get a new state. In the other case, we rotated clockwise. Let's go to another slide. Now, suppose that I rotated this one, the counterclockwise one, back. Let's do that. I'll leave this one alone, but I will rotate this one here, like that. Now I have a state that's a little more special. The only available move on it is this one. If you think of this as a little move in a game, you can rotate clockwise. And if I do that, then I get the one that we drew above. And I have a clockwise move that I can do there. And now there are no more clockwise moves, only anti-clockwise moves. This one, so I say that this one is a clocked state, meaning only clockwise moves. And this is an anti-clocked state. Anti or counterclocked, depending on your English idiom. I like to say counterclocked, I like to say counterclocked because when one speaks in a certain English idiom, one talks about the hand of the clock going around counterclockwise when it goes this way and clockwise when it goes this way. Counterclocked state. So you can start from a clocked state and derive all the other states this way, okay? And then you may or may not recall, but now I'll calculate an Alexander polynomial for you, Conway polynomial. You'll recall that the Conway polynomial, I want to show you how you can use them to calculate Conway polynomial. I think we talked about this before, but I decided to start over. So Conway polynomial satisfies the following identity, that if you take this minus this, you get z times this. And the value of the unknotted circle is 1, and it's an invariant under Reidemeister 1, 2, 3. And that's Conway's formulation of the Alexander polynomial. Actually, we're going to take z to equal to s minus s inverse, and we're going to put labels at the crossings according to this rule. Where S bar is S inverse. And then each state contributes to, I'll draw the trefoil knot over here so you can look at it. You look at the marker and you look back at the knot and you see what the label is on the knot. So let me just do that on these states. So I look back at the knot and I see S. I look back at the knot and I see S. And I look back at the knot and I see 1. Here, S, 1, and minus S inverse. Here, minus S inverse, 1, and minus S inverse. And then you just add up over the states the contributions from each state to the knot. So in this case, we will have delta K, nabla K, is equal to S squared minus 1, SS bar minus minus is plus, S to the minus 2. And you may prefer to see that as S minus S inverse quantity squared plus 1, which is equal to Z squared plus 1, which is perhaps the usual way of writing the Conway polynomial with the trefoil knot. So these states underlie the structure of the Conway polynomial in exactly that way. Okay, so these are very interesting combinatorial states of knot diagrams. We could explain how to get the Jones polynomial from them at another time if you're interested. And the way they're related to the Hagard-Floor homology is more intricate, to say the least. I won't go into it now, but we could try to talk a little about that before the course is over. We won't be complete, but we'll talk a little about it. So, what I want to tell you about is how this gets generalized to knotoids. You might think this would be very special for knot diagrams that are closed, but let's just we have enough time. We have a little bit. We have 20 minutes or so. We'll keep it to 15. Let's take a look at what a knotoid diagram would look like in regard to having states of the same kind. Okay, that's the topic now. But you might want to do another example. So let me give you an exercise. And in fact, I do want to indicate another example. Okay. Let's just draw a random knot diagram here for a moment. Suppose that I'm back at the matter of finding all the solutions to the puzzle. Yeah. So I have my knot diagram, and I've chosen a pair of starred regions, and I try to write down a clock state. And I may succeed, but I'm after writing down a clock state first. So let me just give it a try. If I succeed, then I can show you the next step, but I can also show you how to get a clock state once you found some state. Now that's a state, if I'm not mistaken. And what about its relative clockedness or anti-clockedness? Well, I think you can see that the only move on that game is this one. That's available. It's clock. The theorem is that there's a unique clock state. Theorem I proved a long time ago in a book called Formal Knot Theory. I'll put a copy of the book in Dropbox. There's a unique clock state, and every state can be obtained by doing clocking moves from it. So is this state clocked? Are there any other? I don't think there are at present, other than doing that move, any other moves on this. So we'll label this one 1. And now, having done 1, there are 2 more available, which we'll label 2, level 2. This one and this one. I mean, that's together. Rotate that in, rotate that out. Or you could have rotated this one out and this one in. With this, you could do this. That's a 3. Having done that 3, you could do a 4. But that wasn't all. There was this, or maybe it was in that regard. Let me see. Oh yeah, way over here too, there was a 3, level 3 could happen here. Okay. And then from that level 3, there's a 4. And let's see. There's a 3 and a 2 came together here, you see, and so that could go 4, rotated all the way around back where it was, and the 2 ended up here as a 3. And now, let me see, not far enough yet. We're bumped up in the starred regions. Those are all stopped up. That's probably the end of it, unless I'm missing 1 or 2. If I drew a larger diagram, I could explain to you exactly what all the different states are by explaining that you go to the level 1 and you do this one, that one, that one, or that one. And then from there, you can do this one and you can make a chart. And you can make a chart of all the different possible moves that you can make. And so you can actually enumerate all of the solutions to the Carrollian puzzle, or all the solutions to what are the states, by starting with the clock state and doing a computation of this kind. So you might take it as an exercise to investigate the states of somebody just a little larger than the trefoil, and that would be the figure-8 knot diagram. So maybe this is a good place to put the stars. And the exercise is find out everything about marker states for D above, and delta of E of S for the figure-8 knot, which is the structure over that diagram. Okay, so that's a nice exercise in using this model and finding out what happens in it and how the states contribute and so on. Okay, so now we get to knotoids. So let's see, what is that going to look like? What does a natoid look like? Here's a nice natoid diagram, okay? And if you wanted to make a knot out of it, well, you could do that, right? It's one of the simplest natoids. Remember how natoids work. It's just like knot theory, except that you have endpoints, and the endpoints are not necessarily in the same region. They could be in the same region. That's also a natoid. We call this a knot type natoid because it's really a classical knot. You can connect the ends. But here it's a non-classical classical knot. It's a classical diagram. And you take it up to Reidemeister moves, and you do not allow the arcs to move across the ends. That's forbidden. So we could try to make a marker state here, and we can make a marker state here, but now the story is a little different, because you see, I might put a star here, but this star is actually on top and on the bottom, right? It's everywhere. And so I only have one starred region. And now I have two crossings and two regions, right? That's fine. And I can put a marker here. Oh, but look at that. I could put a marker here. But I could also put a marker here. And that's a single rotate. Like you could go by, you could, if you're thinking in terms of clock states, you could go by one rotation, right? And then you would have this. And then from here, you have an ordinary clocking move, and you would end up here. You see? So there is our counterclocked, our clock state. Let me see. Yeah, that's a clockwise turn. So this is the clock state. This is the counterclock state. And we have to add, we add single turns. And then if you think about it, you'll see that the results are basically similar. Some variations. For example, suppose that I smooth these. Then you see I'm getting a pathway on the basic diagram. This is the basic diagram. I'm not worried about over and under crossings yet. I'm getting a pathway that goes from here to here and never crosses at a crossing. So that's one. And here's another. And there's the third. So the story is very similar. You have a natoid diagram. You have the possibility of running a single trail from beginning to end, never crossing at a crossing. You can think of enumerating all of them, and then the enumeration of all of them corresponds to the single marker states, the marker states, like I have indicated here. And the clock theorem apparently is going through just as before, but we have to add in one extra single kind of clocking move in the middle of things that can happen. And now what about invariants? Well, let's do an invariant and show you how it would calculate, and maybe it's a good idea to use the same board but clear it a little bit. So we have in mind to calculate a Conway potential function defined the same way, okay? Defined exactly the same way, delta K of as a function of S, and S inverse is the sum over the contributions from each state, and the vertex weights for the partition function are S minus S inverse 1, 1 for a positive crossing, and S inverse minus S 1, 1 for a negative crossing. If we don't have time to discuss invariance, we can talk about that next week, but let's just do a calculation so you can see how it works. So this marker is corresponding to a negative crossing, so that's an S bar. This marker is corresponding to a negative crossing, that's an S bar. This marker is corresponding to a 1. This marker is corresponding to a negative crossing, it's an S bar. This crossing is corresponding to an incoming negative crossing, it's a minus S. And this one is corresponding to a 1. So that says that nabla K is equal to S inverse squared minus S inverse minus S. And this will be invariant, but the Skane relation is not in general true. That has to do with the way regions divide up in the combinatorics of it, but it nevertheless is an invariant. And in fact, the fact that the Skane relation is not true leads us to have properties that the Alexander polynomial does not have. For example, you could say, what will happen to this polynomial if you were to take the mirror image? Well, in taking the mirror image, you see, you're going to replace S by S inverse, right? That's what happens when you, so if you go from K to K star, then you will find that delta of K star, the mirror image, as a function of S, is equal to delta K of S inverse. Because that's exactly how it changes. These vertex weights just switch S and S inverse. So if you found that delta K of S inverse was not the same as delta K of S, then you would have shown that the knot was inequivalent to its mirror image. Well, we just did. You see, delta K star for this knot is equal to S squared minus S inverse. This part remained the same, but this part flipped. And so we have actually just proved, which we could prove by other means, of course, that these two are inequivalent knotoids. So this is a generalization of the Alexander polynomial to knotoids. And of course, we are hoping for more. And I will tell you a little bit about how it's going. I'm reporting on research that's actually being done right now. But easy enough to tell you about. So I hope you enjoyed this digression, and we'll continue next week along the various themes that we're looking at. I'll stop here.